Good day. Today, we will be demonstrating the analysis of glass fracture evidence. Our objectives is to examine the physical properties of glass and utilize refractive index comparison to identify and match samples. First, we have a glass. A soda lime glass with the components of sodium dioxide and the refraction index of 1.5. Also, we have a petri dish, hammer, forceps, and magnifying glass, and also marker and clothes. We have also a liquid solutions to be used for comparison of the sample. First, we have baby oil with a refraction index of 1.47, and second is palm oil with a refraction index of 1.458, and lastly, we have a distilled water with a refraction index of 1.333. By comparing the visibility of the glass fragments, especially the presence or disappearance of the Bic line with these solutions, we can accurately verify the identity and origin of the glass sample.
In this scenario, a window at a crime scene has been struck by a projectile, creating visible radial and concentric fractures. The glass have been contained of 6 impacts. Several glass fragments have been collected for laboratory examination to determine the direction of impact and sequence of breakage. The radial fractures, these are the straight lines radiating outward from the point of impact, like spokes on a wheel. They form first on the side opposite the impact. While the concentric fractures, these are the circular or arc lines that connect the radial fractures. These are the lines that give the wave its depth. They form secant and occur on the same side as the first. The first impact, this fracture is the cleanest. Its radial cracks extend for this across the pane without being interrupted. The second impact's radial lines stop abruptly when they hit the cracks from first impact. This indicates that the glass was already separated by first impact, leaving no continuous medium for the stress for second impact to travel through. The stress relief when the first impact occurs, it relieves the internal tension of the glass pane. Later impacts are contained by the boundaries created by the earlier fractures. The third impact, this impact is boxed in. You can see the radial lines stop abruptly when they encounter the B shape formed by the first and second impacts. The fourth impact, these concentric fractures are very tight and limited, filling the small gap between the first and second impact zone. The fifth impact, these impacts fractures are stopped by the existing cracks from the second impacts. While the last impact, this the smallest, like a spider web, its fractures terminate almost immediately against the sprawling lines of the first impact. When a bullet strikes glass, the characteristic of the hole changes significantly depending on the distance of the shooter and the velocity of the projectile. The entrance hole, the side where the bullet first makes contact, it is typically smaller with cleaner edges and flake. Exit hole, the side where the bullet leaves the glass, it is wider and cratered. This happens because the pressure of the bullet pushes a larger cone-shaped piece of glass out of the back surface. The close range, when the gunshot is from a close range, the bullet is traveling at its maximum velocity. This results in very distinct clean impact. The entrance hole, it is usually small, circular, and very neat. Because the bullet is moving so fast, the glass doesn't have time to deform or shatter extensively before the bullet passes through. While the exit side, you will see a coned or cratered effect. The exit side of the hole is always wider than the entrance side. This is known as spalling, where the pressure of the bullet pushes a cone-shaped plug or glass out of the back. Fractures lines, you will see a high density of radial fractures radiating out from the center, and concentric fractures, circular lines around the hole. The long range As the distance increases, the bullet loses kinetic energy and velocity. By the time it hits the glass, it is slower and may have begun to tumble or lose stability. The entrance hole, instead of clean circle, the hole becomes irregular and larger because the bullet is slower. The glass has more time to flex and shatter upon impact. This is higher likelihood of the glass spider weaving or collapsing entirely. You won't see the same surgical precision found in a close range shot. The coning effect on the exit side is still present, but it may be asymmetrical or jagged because the bullet's angle of entry is often less stable at long distance. The trial rule for forensic analysis, regardless of the distance, forensics investigators use the trial rule to determine the direction of the shot by looking at the radial fractures. The radial fractures form right angles on the right side of the glass. By examining the cross section of our fracture line, the rib marks or ulnar lines, an investigator can confirm if the bullet came from the front or the back, even if the distance made the hole look messy. To determine if a glass sample from a suspect matches a known source, we look for the Bicky line to disappear when the refractive index of the glass and the liquid match perfectly. The glass becomes invisible because the light does not bend as it passes through